All right, let's talk about AP Physics C E&M 2024 actual exam, set 2, question 1. A non-conducting rod of uniform negative linear charge density is near a sphere with a positive charge. So this is where the rod is, this is where the sphere is. And the rod and sphere are held at rest on the y-axis. Equipotential lines are, and the positions are labeled. Adjacent tick marks on the x and y-axis correspond to 0.4 meters. However, the absolute value of the electric flux through the Gaussian surface whose cross-section is the 0-volt potential line. Where is the 0-volt potential line? I think I can see it over here. And what is the Gauss's law? Gauss's law is that the electric flux is equal to Q inside over epsilon naught. Since we are only looking for the magnitude, so I'm just gonna place an absolute value sign around Q, although it doesn't really matter because Q is anyway, the sphere's charge is positive anyway, so it doesn't really matter. So 1 nanocoulomb means nano is 10 raised to negative 9 over epsilon naught, and epsilon naught is given by 8.85 times 10 raised to negative 12. So this comes out as 112.994, and flux is E dot A. E is Newton per coulomb and area is meters. So Newton meter square plus Newton meter square per coulomb. That is the value of the flux for part A. The next one says that a positive test charge not shown is placed and held at the position C. So I think I'm going to need that figure once again. Let me borrow that real quick. Okay. So we have a test charge at C here. That test charge is positive, and it is moved to different positions in this particular fashion, like C to E, to D, E, D to A, so C to E, E to D, and then D to A. The bar shown in figure 2 represents the absolute value of the work done by CE, that is to move from C to E. Okay, so from C to E, some work was carried out. Okay. Now calculate a bar, draw a bar to represent the relative absolute value of the work from E to D and likewise from D to A. If any of the work is 0, then just write 0 in the corresponding figure. So let's first, in fact, do you guys think there will be any work from E to D? I don't think so. Not because it is at 0 volt, but because E to D are on, E and D are on equipotential lines, equipotential line. And what is the work done formula? Work done is given by Q times, the absolute value of the work done is given by Q times absolute value of delta V. And since E and D are on equipotential line, so there is no delta V. So delta V is 0, which means the work done is 0. So from E to D, for sure, the work done is 0. So I'm just going to write 0 over here. From D to A, yes, there will be work because it's going from 0 volt to some other volt, which is minus 10 volt. So the work done from D, from D to A, absolute value again is going to be Q times 10 volt, because this is 0 volt and this is minus 10 volt. So the difference absolute value is just 10 volt. So this is 10Q. But we need to draw relative, the height of the bar should be relative to the first one. So we need to get the value of WCE as well. And WCE will be Q times, I believe C is at minus 20 volt and E, right? E is at 0 volt. E is at 0 volt. So difference between negative 20 and 0, absolute value again is 20. So that is 20Q. So if this represents 20Q and I need to draw a 10Q, obviously that's going to be the half. So half of it, since this is covering 1, 2, 3 blocks, so it should cover 1.5. So 1.5 will be around here. That should be the work done by dA, absolute value relative. Okay. The next one talks about calculate the approximate magnitude of the x component of the electric field at position B. Again, I'm going to borrow this figure. So at position B, they are talking about the x component of the electric field. Position B is somewhere over here. It's exactly here, actually. How will we find the electric field here? I think, we can use the, huh, interesting. So, although it doesn't really matter whether we take B as a reference or perhaps this point as a reference, because I don't really know the potential at B, right? But I for sure know that whatever is the electric field in the X direction, there has to be constant because of this, right? Because the voltage is decreasing in the same fashion. And anyway, they're asking about the approximate magnitude. So we can perhaps take this and this, these 2 points as reference point and use that electric field magnitude. So magnitude is just delta V over delta X, and that will give us the approximate value. So what is delta V? Delta V between these 2 points is this is at -20 and this one is at -10. So the difference is going to be just 10, absolute value once again. And the delta V, delta X. So this is zero point 0.4, this is zero point 0.4, this is zero point 0.4. This will make 1.2, and this is approximately half of 0.4. This is zero point 0.2. So 1.2 plus 0.2 is 1.4. 10 divided by 1.4 is 7.14 volt per meter. That can be the unit, or you can write the units as Newton per coulomb. That is also an acceptable unit. So this is the average value of the electric field in the x direction. Okay. Now they're talking. Now they're okay. A positive test charge is placed at C. Once again, I'm going to borrow. Okay, so here they're talking about a positive test charge is placed at C. The test charge is then released. Indicate the direction of the net electric force exerted on the charge immediately after it is released. Okay. We for sure know that and directed away from the sphere towards the sphere. We for sure know that it has to be perpendicular to the electric field lines because, sorry, the equipotential, because that's the property, right? Electric field lines are always perpendicular to the equipotential lines. So it has to be like this right after that. The only question is whether it is going up or whether it is going, whether it's going up or whether it's going down. So one way to understand is this is positive, so it's going to repel. So it doesn't make any sense that it will go up. It has to come down. So it has to be towards minus y-axis, and it has to be directed away from the sphere. That's one way to understand it, because we have to justify it as well. Another way to understand this is the first justification we have already given, that E is perpendicular to equipotential line. The second reason of pointing downwards is that the test charge and sphere repels repel each other. That can be a reason, or you can also say that the electric field always points from higher to lower potential. So you can clearly see that this potential is -20 volt, and here we are going towards the lower potential, so it has to be towards the minus y-axis and has to be directed away from the sphere. So any of these two reasons which are wrote in point 2, that would make sense. So this is what we have. All right, the next one is the sphere and the test charge are then removed, and the rod of length 2L and a uniform negative linear charge density negative lambda. The rod is held at rest, and we need to, and there is a point yp on the y-axis such that it is greater than 2L. The potential at that point is given by this expression, so we need to derive this. Okay, all right, we can do that. First, let's take an elemental charge over here, which is dq. And from dq, let's go to some distance r, where the yp is located. So what will be the potential at yp? dvp, elemental potential, is going to be k dq over r. What is dq? dq is obviously the linear charge density, which is minus lambda times this thickness, and this thickness is just dr. Uh, no, the thickness is just going to be dx because we are taking x as a parameter because we are coming from here at a distance of x. So that's going to be dx over r. But obviously I cannot integrate this because how can I integrate dx operand with r variable? So we need to convert r in fact, x won't make sense, right? I think dy will make more sense. Let's try dy. Because this is like in the y-axis, although it's not like dx will be marked incorrect, but it's more intuitive that it should be taken as y. Okay, so we have this over r, but now we need to rewrite r in terms of y. So we know that this entire thing is yp, which is to be treated as a constant, and this teeny tiny thing is y. So this remaining thing r is going to be the difference between yp and y. So this comes out as negative k lambda dy over r is replaced with yp minus y. Let's give this negative sign, let's multiply this negative sign to this one. In other words, let's take negative outside from here. So the negative will be gone and this will swap the sign, and now we can just integrate on both the sides. The left side will just be Vp. K lambda as a constant comes out. A dy over y minus p is natural log of absolute value of y minus yp, having the bounds from, what are the bounds of y? It's from 0 to 2L, right? Because this is till where the rod is, so 2L. So I'm going to place the upper bound here, which is k lambda times ln 2L minus yp minus ln, forgot to place an absolute value here, absolute value, and then absolute value of minus yp. Okay, well, let's borrow this on the next page. Running a little short space here. All right. This can be written as k lambda natural log of, I think I will write yp minus 2L and do away with the absolute value because it's given that yp is greater than 2L. It will make more sense, and minus natural log of yp. And what is log a minus log b? I think, what do they need, by the way? They need a negative sign outside, and by the way, they need yp on the top. So it will make more sense if I take a negative as a common factor. So minus comes out, and I'm left with ln of yp minus ln of yp minus 2L. So this will come out as minus k lambda, and log a minus log b is log of a over b, which is yp minus, or yp over yp minus 2L. And this is exactly what they needed from us. So this is the final answer. Let's box it up. Finally, they are asking us to sketch a graph of the y component of the electric field from the rod as a function of y. Okay. So we already have the potential, and we can easily find the electric field from the potential, right? Let me borrow this expression because that's going to be helpful for us. So this is the expression for the potential, and I know that the electric field is given by negative of dv over dy because the y is the parameter. So this is just a general point yp. So obviously we are going to treat this as a general point y. So that's going to be minus k lambda natural log of y over y minus 2L. That's what we have. Okay. Negative k lambda comes out, and the double negatives become positive. So the electric field will be k lambda derivative of, and at the same time log a over b is log a minus log b. That will just make it a little easy for us to find the derivative. All right, let's take this to the next slide. So this is what we have. Okay, let's find the derivative now. So that's going to be k lambda. The derivative is of ln is 1 over y, and ln of y minus 2L is 1 over y minus 2L. This is the electric field. Now the question is, how will the graph look like? One thing is for sure, that since it starts from 2L, I know that at 2L, this is going to be 0. So that's going to go till negative infinity, because when I place 2L, 2L minus 2L is 0 and 1 over 0 is infinity, but remember there is a negative sign outside. So I know that it's going to treat this point as a, I mean, I can obviously take it on the same page, but prima facie analysis suggests that the electric field must start taking 2L as a vertical asymptote and going something like this. But once again, you can use a calculator as well, and I'm going to show you how. So what I did is I plugged this expression in the calculator, and this is what we have. Uh, all I did was I replaced that k lambda with 1 and 2L as well with 1. So the expression which I have graphed is, obviously I just replaced y with x, so it doesn't really matter. So 1 over x minus 1 over x minus 1 to get the trajectory. Now, you can clearly see that about x equal to 1, and this is where we are interested in. X greater than 2L, and our 2L is just 1, so x greater than 1, and like we predicted, it's going from negative infinity and coming eventually downwards. So that's how the graph is going to look like. It will come from negative infinity and eventually come downwards, and we need to graph till 12L. So it will just keep coming like this, and will stop somewhere at 12L with some value. So that's how it is going to look like. I hope this makes sense. Any questions, please post it in the comment section. I'll see you in the next video. Bye-bye. Initial share of RA will obviously decrease, right? Because that is going to be shared with this teeny tiny another resistor as well. So it makes sense that whatever delta V2 is, I'm not really interested to calculate. That has to be a little less than V1 because of the introduction of this new resistor in the circuit. So I think option B makes most sense. All right, so this is how we do this question. I think this was the last part, is it? Yeah, that was the last one. So I'll see you in the next video and another question.